All right, Pathways problem 10.2. This is a really nice problem because it allows us to kind of explore writing these Lewis structures and also something called resonance hybrid. Now, it's a problem that's early on in your book, 10.2. It's only number 2, but believe it or not, it deals with some advanced concepts from this chapter. The problem asks us, when is a resonance hybrid needed to adequately depict bonding in a molecule? Using NO2 as an example, explain how resonance hybrid is consistent, actual bond lengths and bond strength, bond order in this molecule. So this is actually, this idea of resonance hybrid is kind of an advanced concept for this chapter, but it's actually pretty important for not only this class, but as you proceed in chemistry and get into organic chemistry and so on and so forth. So I wanted to tackle this one, right off the bat to try to explain this. And this problem is, we're going to try to get at correct answers, but it's really a little bit more of a tutorial than anything else, okay? So when you're coming up with the resonance hybrids, what you're really needing to do is come up with all of the possible Lewis dot structures for the molecule of interest. And here it's NO2. So the first step in coming up with a Lewis dot structure is always the same. It's taking your valence electrons, adding them together. This kind of gives you the ingredients for what you got to work with, because remember, these valence electrons are kind of like the ingredients to our bonds. And nitrogen's got 5. We can tell that because it's in group 5 of the periodic table, and each copy of oxygen's got 6. You add them together, you get 17 electrons. Now this is an odd number of valence electrons, which is a little bit unusual, I think. So that tells me kind of right off the bat that something a little bit strange might be afoot here. But nonetheless, we proceed in writing the Lewis dot structure by following the second step. Okay, now the second step for writing the Lewis dot structure is coming up with connectivity for the atoms. I've chosen to put nitrogen in the center and oxygen on the outside. The reason why is because the element with the lower group number or lower electronegativity usually goes in the center, and that serves as our central atom. For these particular pairings of atoms, nitrogen is in the lower group number, so it's going to go in the center. Okay, so I put that right in the center to begin with. I have one line or bond here, one here, which is the minimum required to hold these atoms together at first. So if we try to complete the Lewis dot structures, then what we would do is go about assigning electrons to complete the octets of all the atoms. So I'd have, since each line represents 2, I have to do 6 dots on this oxygen. Now that's got 8. I have to do 6 dots over here. Now that's got 8 with the bonding. Alright, so that's 6, 6, 2, and 2 for each bonding pair. Alright, so where are we at with that? Looks like right now we're at 16 electrons, so we've only got one more to use, and I'll put that there in the center of nitrogen, okay? Now let's evaluate the structure. That's our last step to see if it makes sense. Now the oxygen should be reasonably happy, I guess. I mean, I've got 8 electrons that they're taking part in. But I've got a little bit of a problem, I think, with the central nitrogen. The nitrogen's got 2, 4 that it's taking part with this extra. But right now, that's only got 5 valence electrons that it is sort of partaking in, if you want to think of it that way, okay? And this is a little bit of a problem, okay? Because, well, we would like to complete its octet if at all possible. So I don't like that. I think there might be a better way to arrange these atoms. So for instance, maybe what I could do is share more electrons. So I'm going to write my nitrogen in the center. Maybe I could do 1, 2, 3, 4, 5, 6. 2, 3, 4, which makes 10, 12, 14, 16, 17. Okay, so now, let's see, I've got 4 more, that's 8. Got 6 and 2 is 8 for the oxygen. Nitrogen's got 6 plus 1, now at least it's got 7, which is better than 5 in terms of completing its octet. So this is a little bit better solution than what we had up here, okay? Now, are there still limitations to it? Yes, right? For instance, we've got this 1 electron. If I could add a second one here, then that nitrogen octet would also be completed and it would be happy, right? But the problem is I don't have 18 electrons, I only have 17. okay? So I can't really do that, right? And there's this vacancy right here. Now that vacancy is kind of important in chemistry, right? Because what it does is on that central atom, as I have it drawn here, is it creates an unpaired electron. Okay, that's one interesting thing about this structure, okay? Unpaired electron. Whenever you see Lewis dot structures like this, and it could be centered on the nitrogen or else on the oxygen, we'll get to that a little bit more in a little bit. But whenever you see that vacancy or an unpaired electron, you have made something called a free radical. You made a free radical. Free radicals are very, very, very reactive in chemistry. And the reason why is because they've got unpaired electrons residing somewhere in the structure. That atom's not very happy about that, and it's always seeking electrons by reacting with other substances. So if you ever hear that term free radical, that's ultimately what it comes down to, is it's a chemical compound with unpaired electrons in the dot structure. Very reactive. Okay, so that's the first thing that's kind of interesting about that. And I suspected that maybe we would come down this route when I saw that we had an odd number of electrons to use to write our dot structure. But nonetheless, that's one thing that's interesting about this. Okay, now, moving on. About this Lewis dot structure, okay? Seems like this is one way I could write the Lewis dot structure, where this double bond was on the right instead of on the left. But another way, I think I could probably write it, would be to choose to write the double bond on the left and the single bond on the right. I can move around, if you will, where the double bond is. Okay? So that would seem to be as valid a structure as the other one. And I think I might also potentially choose to do something even wholly different. Keep pay close attention to the electron dots here, okay? Maybe I could put 2 electrons on the central nitrogen. And if I did that, I completed its octet, but it has to, that second electron has to come from somewhere. Okay, so maybe I'll just steal one of these off of this oxygen and put it there instead. Okay? And I guess there's a number of other possibilities that you could even envision beyond that. Maybe I'll do even something like this. I mean, if I'm just kind of brainstorming ideas here. Okay, something like that, where now I steal the electron from the double bonded oxygen and put it on the central nitrogen. All right, and of course I could flip-flop the double bond and steal electrons from different places, okay, so on and so forth, right? So I guess what I'm getting at here is that this NO2 molecule can actually, theoretically at least, exist in many different forms. And I think all of these have the same number of valence electrons, right? 6, 8, 10, 11, 13, 15, 17. That's got 17. 2, 4, 6, 8, 10, 12, 14, 16, 17. They've all got 17. So I haven't really violated any hard rules in terms of how many electrons I can use. So there are many possible structures that this molecule could potentially exist in. Now, some might be chemically favored versus others, but nonetheless, these are all kind of at least possible. So what is the true Lewis structure for NO2? Well, that's kind of a complicated question because I can't really disprove any of these. So you see this word resonance hybrid? That's kind of the interesting idea here. A resonance hybrid is basically a theoretical blending of all of the possible Lewis dot structures for a particular molecule. It's a theoretical blending of all of the possible Lewis dot structures. And the interesting thing about it is none of the dot structures necessarily are perfectly correct, or the one that is always true, okay? Instead, the true molecular structure exists as a hybrid of all of the possible cases. And this is very interesting. And what evidence do we have that that's really true, that we get this hybrid business, okay? Well, this question goes on to ask about bond lengths, and bond orders, average bond orders. These are characteristics of the molecule that might be measurable, okay? Think about bond length. That's just the length of the bond between the atoms, between the nitrogen and the oxygen. It turns out that if I go into the lab and I try to measure and study what the bond lengths are between these two bonds, I find that experimentally they're identical. I can't necessarily tell the difference between this bond and that bond experimentally. They're identical. And that's interesting because, I mean, if you think about the Lewis dot structure, I mean, if I have this case, this is a double bond, this is a single bond, these two bonds should appear different to me experimentally. This bond would probably be a little bit stronger and shorter, and this one would be a little bit longer and weaker. But if I go into the lab and I measure the molecule experimentally, I see no difference between the two. Same thing with bond order. If I try to figure out, oh, is this a single bond, double bond, is it here or is it here? I go in the lab and I try to make measurements, no difference between the bonds, okay? I might get an average bond order of 1.5 for my molecule, essentially halfway between a single bond and a double bond. I can't tell the difference between the two. I can't tell where that single bond is and where the double bond is experimentally, okay? And that's not necessarily because I'm limited with my precision of measurement. It's because the molecule actually exists as a resonance hybrid. It exists as this bond having a bond order of 1.5 and this one having a 1.5 character. But the truth of the matter is somewhere blended between the two. In this particular case, I guess that would be between these two particular structures. But to be honest, this business of moving the electron around between different locations, like when it's in the oxygen and the nitrogen, that's also blended in to this resonance hybrid, okay? So the truth of the matter is that the molecule exists in the form of these resonance hybrids, which is a blending of all the possible Lewis dot structures, not one particular case, okay? Now there are some rules or approaches that can be used to figure out which of resonance hybrid tend to be the most important structures. And this approach is assigning something called formal charges. Okay, this is outlined in your book. And if I'm going to give you kind of a quick overview of how to assign a formal charge, a formula to do it, the first thing that you do, and you can do this for every atom in the structure, is you got to figure out how many valence electrons are given to that atom on the periodic table. Okay, so for instance, I can assign a formal charge for this oxygen atom right here. Okay, so since we're talking about oxygen's got 6 electrons on the periodic table. or 6 valence electrons assigned to it, given its electron configuration based on its placement in the periodic table. Now, what I have to subtract from that is the number of electrons essentially given to it in a structure. Okay. Now, that's a little bit more complicated because there's different types of electrons, right? There's bonding electrons and there's non-bonding electrons, okay? So there's two different types. Now, if you've got a non-bonding electron, like these dots, that's assumed to be wholly the property of that atom. So this oxygen's got 1, 2, 3, 4, 5 non-bonding electrons that belong to it, right? But it's also got a bond. Now, in formal charge calculations, we assume that the electrons that are involved in this bond are shared equally. That means that 1 gets assigned to nitrogen and 1 gets assigned to oxygen, okay? Because again, that we consider it shared equally, and that bond is consisting of those 2 electrons, right? So based on that, then, it looks like 6 electrons are assigned to it, and my formal charge here is going to be a big fat 0, okay? Now, having 0 formal charge actually tends to be a good thing, okay? That's a good thing for atoms and structures. 0 formal charge is what we want to shoot for. Now, let's calculate the formal charge for this other oxygen. Okay. 1, 2, 3, 4, 5, 6. The placement on the periodic table says 6 with the sign 6. Also have 0 for that one. Okay. Now, what about the central nitrogen? 5 from the periodic table. 1, 2, 3, 4, 5. Well, okay, good. Formal charges are zeros. Okay, that's generally, again, a good thing. It turns out that the sum of all the formal charges for a structure also needs to be the charge on the molecule or ion. So here I add 3 zeros, and there's a neutral molecule, which is consistent with the structure, and that is, of course, a good thing, right? Now, what about assigning formal charges for this structure here, okay? So, again, formal charge for this oxygen, the placement on the periodic table for oxygen says 6, so I do 6 minus whatever I've got. Well, I've got 6, 7, so it looks like, boy, the formal charge here is minus 1. If I do it over here, I think I get a formal charge of 0, because 1, 2, 3, 4, 5, 6, that's what's assigned on the periodic table, so no big deal. What about this central nitrogen? I have to do 5 minus something. It looks like 5 minus 1, 2, 3, 4. So 5 minus 4 is plus 1 formal charge. So I've got a minus 1 and a plus 1. It still sums to 0, which has to be the case because it's a neutral molecule. But the presence of formal charges usually says that that's a less preferred structure. Okay, so kind of keep that in mind. So this is one tool that we can use for figuring out which of these resonance forms in the resonance hybrid is in fact most important for a particular molecule. So this is only problem 2 in the chapter, but as you can see, there's very important ideas here, okay? Not only we talk about writing Lewis structures, but we talked about this idea of a resonance hybrid, whereby the true molecule exists as a blending of the different resonance forms or different Lewis structures that are all valid that the molecule can exist in. If I tried, I could not measure a difference between these two bonds. They would appear to me as being the same. And the reason why that is, again, is because the molecule exists as this resonance hybrid. That's our model for it, okay? You cannot tell the difference in bond length or bond order, bond character between these two locations. They would appear to be the same. And that provides experimental evidence for the truth of this idea behind resonance hybridization.